this is the very, very rough version of a AGU Fellows seminar that I'm supposed to be giving this year. So you get the first version. It's a good thing because it was far too long and I've shortened it, but it still needs to be improved. And Bridget Scanlon is also one of those seminar speakers. So the Jackson School is well represented in that program. What I'm going to talk about today is sort of a history of my journey studying the construction and destruction of coastal zones. And I have been doing this for a while. I should also point out the work that you're going to see is really the work of a number of my graduate students, and I was just fortunate enough to be able to tag along. But I am going to try to put it all together into an interesting story for you. So I was a brand new assistant professor just coming back from industry when Hurricane Katrina struck. And I had an opportunity to totally change what I actually did scientifically. And I chose to do exactly that. So the impacts of Hurricane Katrina on Louisiana have had a profound influence on my scientific career. And we got into it quickly. Within a month, I was part of a large multidisciplinary team studying the Mississippi Delta in particular, but coastal systems in general. And just to motivate that, here are some of the remarkable deposits that actually buried cars and houses in New Orleans as the levees buried them with sediment, and some of the beautiful stratigraphy associated with those burying deposits. So what really got us going, at the same time, the USGS published what is now a very famous map that showed in red the areas that where there had been land loss in since 1932 to 2000, and a few places in green, like right here that we're going to focus on in just a minute, where there's actually been land gain. And between the hurricane and this sort of data analysis, there were a lot of people that were really thinking, well, there really isn't much we can do about the Mississippi Delta. And these were people that honestly should know better. So Bruce Babbitt, who was 8 years the Secretary of the Interior for Bill Clinton, said in 2007, not that long after Hurricane Katrina, that most of the Mississippi will inexorably sink beneath the waterways by the end of the century. So the question is, should we try to do something, or is there nothing that we can do? Well, I knew, because I was trained as a sedimentary geologist, that there are plenty of coastal zones that have been very healthy and actually have migrated seaward under sea level rise rates that are quite a bit greater than what we have today. So it isn't just, sea level is rising is high, or relative sea level that we'll talk about in a minute is high. It's more complicated than that. It's a dynamic surface. It's not just a platform that sea level and subsidence act on. It actually changes shape. And here are just some of those examples, from Ron Steele, if you remember him, in Spitsbergen, looking at continental scale margins in outcrop. Here's seismic data from the North Slope of Alaska, and here's a little experiment. So I knew that couldn't be the case, and we wanted to understand what could potentially be done, but we didn't know much about how these fine-grained, low-relief systems worked. So we started to study them. And we began, when you don't know much, by saying, well, what are the parts that go into a mass balance that sets what the coast is doing? And others have done this mass balance too, but this is the one that we used. We had here on the left-hand side of this simple equation, we have sea level rise rates, we have subsidence, land surface subsidence rates. Those are multiplied by an area of coast. And that's the sink. That's the collector that creates space. And then we have some terms over here, and the important ones. One is the the volume of sediment, the discharge of sediment coming in, the fraction of it that's actually getting captured near the coast. Because you can have a lot coming in, and if it all just keeps going somewhere else, it doesn't go into maintaining the resiliency of the coast. And then you have one here that we know a lot less about, which is the vertical accretion rate of organic material. And those pieces act to balance the sea level rise and the subsidence. So we want to explore all of those things, and we'll start with the space creators. And we hear a lot about sea level rise all the time. And I think we hear a lot about sea level rise because we actually understand it better than any of the other terms on that equation. And because we understand it and can measure it better, we talk about it a lot. And we have, through satellite altimetry, we get these incredible maps looking. This is a sea level change rate map that you see right here. You can see the particularly high changes happening in the Gulf of Mexico. These, of course, are now referenced in this case to the center of the Earth, but also in other cases, it can be to a geoid. And then we have some of the remarkable INSAR data from Ann Chen's group here at the University of Texas, where they're actually using radar interferometry to look at changes in land surface elevations over time. And it's interesting to note that over this interval of time in the 2017 to 2020, the subsidence associated with groundwater withdrawal in Katy matches or exceeds subsidence associated with the Eagle Bird play. So we have some pretty amazing things. And you can see that there's some large values of subsidence, the reds, along the coast here. So if you sum the sea level going up and the surface going down, in the Gulf, it could be as bad locally as like 2 centimeters a year of space being created. So that's a lot, and we'll talk about what that means in just a couple minutes. Now, the other term on the sort of sink term is the subsidence, and I'm fortunate that Jack Sharp, the speaker last week, spent a lot of time referring to this. The thing about subsidence is that it really, really depends on where you're looking locally, and then you have shallow subsidence, you have deeper subsidence, and you have geophysical subsidence. All of these things act, and they're all driven by different mechanisms, whether it's just gravitational compaction of deposits, withdrawal of subsurface fluids, which Jack was talking about, or just long-term geophysical subsidence due to loading. And so it's really hard to talk about subsidence intelligently to the community, because the rates, and I plotted here sort of typical maximum rates as a function of time scale. This is all data from the Mississippi Delta. The rates go from values that are a couple tens of centimeters a year due to displacements on individual growth faults to rates of tens of millimeters a year associated with subsurface fluid withdrawal to longer term compactional processes at the sort of the millennial scale. And finally, at the geological scale, you get down here to just fractions of a millimeter when you're averaging over hundreds of thousands of years. So that's a 3 order of magnitude, 1, 2, 3, almost 4 order of magnitude change. So you've got to be really careful. And people spout out, I've been to meetings where they talk about this is the representative rate, or the one up here, which it isn't working now. So I'll see if it works here. Up here is the representative rate. So we just have to understand what time averaging window we're talking about. Now, I mentioned those faults, and just to show you an example of these, here, this is Galveston County, Texas. These are faults that you couldn't see 60 years ago. I've highlighted them there and shown the down-thrown side, and then I'll turn off them, and you can see, oops, if we go back, you can go back again, you can see where they are, and you can see where they go. So these things have surface displacements that are real. You can see them in satellite imagery. You can go out and see them in the field. And so we can get locally very, very high rates indeed. But for the rest of the talk, due to time, I'm not going to spend much of it on the sink terms. I want to talk about the source terms, the space filling terms, because that's what really got us going after Hurricane Katrina. It's like, well, do we understand what's being delivered and what the organic material is actually doing to fill that space associated with relative sea level rise? And so there are a couple things I need to explain to you about these large lowland rivers. Now, this is the Mississippi, and this long profile looks like a cartoon, but this is actually data. Each one of those diamonds is a gauging station on the Mississippi. This is actual bathymetry from the Mississippi. You can see the Mississippi's river bottom. It takes over 600 river kilometers before it rises above sea level. It's a very remarkable system. And this is what the water surface profile looks at a low river discharge. And how does sediment move through a system like this, where you have this incredible change in surface slope and incredible deepening associated with the water entering the Gulf of Mexico itself? Well, that's what it looks like at high discharge then. So we've gone from low discharge, which I just showed you, which is now sort of the purple gauging station values. And here are the stages associated with high discharge. And you can see what happens is that the slope of the river literally steepens. So most of the time when we think about floods, we think about water levels going up and things getting inundated. In this zone of gradually varying flow, as these rivers, these low gradient rivers come out to the coast, it's actually about steepening up the slope of the river. You don't actually have much of a flood. You can see that the water levels actually aren't going up very much at all in the lower Mississippi. What's happening is, because of that slope increase, the velocities are going up. So if you look at this plot right here, in squares is our data from New Orleans, which is at 160 right here, and in diamonds is data from Tarbert's Landing, which is this right here, this river kilometer 487. And you can see that at low discharge, why is this getting lost? Yeah, low discharge, there's a pretty significant deceleration. The velocities go down as you go downstream, and they reverse each other at high discharge. So what happens is it's really hard to get stuff out to the end of the river during low discharge. In fact, you don't get a lot of solids out. And then it accelerates, and so everything blasts through and goes all the way to the coast. So it's a really different kind of threshold system that we weren't expecting to see in a perennial river. And so we were taking this insight then to the two places on the famous USGS map where a lot of land is growing, the Atchafalaya Delta right here, which is the older and larger of the deltas, and then the Wax Lake Delta, which was associated with a man-made cut that was supposed to alleviate flooding in Morgan City. The Wax Lake Delta has sort of been left to its own devices, so it's a wonderful natural laboratory. So we went out there to specifically look at, what is the sediment time, the discharge, how does that work, how much is actually being trapped, and what can we say about this vertical accumulation rate of organic matter? Because those are the things that can help us build land. And this delta, the Wax Lake Delta, since its origin is man-made, we know exactly when that cut was made. And so all that land has been built in just the last 70 years or so. So it's a great place to go study. So this is what the end of the delta looks like. And it doesn't look like you're building land at all. You look like you're just out in the Gulf or like a kilometer away from anything that might be considered land. And our multi-beam system, it's hard to make measurements in water this shallow. So we don't have a lot of measurements. All of our oceanographic tools simply don't work in a meter of water. So we built our poor man's multi-beam system. John Shaw, who is the leader of that, is in in the boat, thinking bad thoughts as the system is not working. And Travis Swanson, who some of you may remember, is just enjoying a little respite in the Gulf of Mexico and Chafalaya Bay. So if we come out of the delta, way out to the tips of the river channels, you can see in this profile that the river channel itself climbs up slope all the way to the end. So these channels are much, much deeper than sea level, and they shallow all the way up to the end. And we wanted to know how they worked and how they built. So what we did using this system that John built is to collect multiple bathymetric surveys at very shallow depths over multiple times, of which I'm only going to show you 3. One from July 10, where we're coming out of a flood and we're going into a period of low discharge between July 10 and March 11th. So we'll look at the difference that happened then. And then we'll look at what happened between March 11th and August 12th, where there was a big flood. And you can see here the suspended sand concentrations. There's really nothing happening during this low flow period, even though no one would think of 2,000 cubic meters a second of water as low flow, except in the greater Mississippi system. That's a remarkable amount of water. And then the concentrations go up of suspended sand, but still they're very, very low concentrations. One of our big problems in this project was we don't actually measure the stuff that builds land, which is the stuff that's moving as bedload. The USGS measures suspended load, and they are not close to the same thing. And it's really hard to use a suspended load and say anything about what the bed load actually is. So we have put ourselves at a disadvantage as a country by not having a program that does that in a systematic way. I mean, the argument is, well, there's a lot more suspended load moving through the system than there is bed load. That is true. It's like 10 to 1. But if you actually are looking at what makes the topography and what builds the land, it's the coarser material that we're not capturing properly. But here's what happens between those times. So this is at the end of one of the floods in July 2010. This is the very tip of one of the distributary channels. And here's what it looked like after a number of months of low flow. So that was March 20. So again, July 10, March 20, July 10, March 20. So we were incredibly surprised. There's an etching and a definition of the channels developing here. No sediment is being added, but the channels are being better defined by tidal current, waves and tides moving sediment a little way. So that's what we had going on during the low flow, and then this is what happened during the high flow. So that's the low flow, these beautiful channels. And then here after the flood, you can see a lot of the channels have left because we're in this little box area right here. It doesn't even look like we're on land. And we're just left with with a big dump of sediment and many less channels associated with it. And if we make difference maps of this, you can sort of see what we have. We have a lot of, it's net erosional during low flow. And it's actually balanced, because if you add it all up, the sediment's going into defining the edges of the channel and it's being eroded other places. So really it's just getting reworked little ways. And then during the big flood, sure, you erode the primary channel, but there's a tremendous amount of deposition. So we have a lot going on, but it's not going on most of the year. And that's not how we usually think about sandy perennial rivers. We think about sort of continuous transport of sediment. We don't think about nothing and then a lot. So that took some redoing. And then there's another interesting thing here to go with what happened, the connection between the channels that are building the land and the coarse material that is building the land, which in this case, by coarse material, I mean like fine and medium sand. If you take a profile off that channel pass that we just showed you, the channel tip, and we just go out to sea, this is what the topography looks like. And you can see that within half a kilometer of the tip of that channel, all that's left is muds. So all of the sand, all of the coarse material is being scrubbed from the system, which is interesting. And that's why when you look at deposits of the Mississippi over long time scale or the Wax Lake over multi-decadal scale, even though the sand may represent at best 10% of the solids going down the system, it represents at least 50% of the deposit. So it really is enriched in the sand, and it's important to understand what the sand is doing. But was worrisome because if we're scrubbing, if there's only half a kilometer left before we're out of sand, is there any chance of maintaining this delta or growing this delta? And this is where another term in our mass balance comes in. You can see this is here's the sediment discharge. The fraction of sand is, it's all getting caught in this particular delta. But not all the mud is getting caught. So is there something that might help you capture more of the mud in the system? And what about the organics? Well, it turns out the organics help a lot, and they help a lot in ways that we do not understand yet. This is a major part of the land building problem that ecologists and geomorphologists need to spend a lot more time talking with each other about. So here's a picture of Wax Lake Delta going from the apex here down toward the end of the delta. This is over 8 kilometers right here. And of course, as you go from the upstream end of the delta to the downstream end of the delta, you're actually younging from about 35 years ago when this paper was written in 2013 to 10 years ago. But as it youngs, or more importantly, as it ages, the fraction of organic material in the greater soil column is going up substantially. And it's even more so if you go over to the Atchafalaya Delta, which is considerably older than the Wax Lake Delta. You have peats actually beginning to develop. So you can see there are whole intervals that are very organic rich, and here's, of course, a peat growing on top of the delta. So my friend and colleague, Robert Twilley, who's an ecologist at LSU, said something a long time ago that has always influenced me. If you're in the game of building land by delivering sediment to the coast, the rivers build the land, but the plants maintain it. So you bring in and you make the substratum that the plants live on. And then the plants in a place like the Gulf of Mexico, the vertical accumulation rates can be as much as 2 centimeters a year. And so they can make a lot of vertical maintained against sea level rise, but they can't go on forever. And one of the great unanswered questions is what happens if this term actually exceeds this rate? Well, then that whole term that may have been contributing a lot to the system gets X'd out, and then you really may have an unzipping of your coastline. But this is something that still needs to be done. And August Alto, who's a graduate student at the Jackson School, is definitely doing some of this kind of work. Okay. This is not a fun story, it turns out. I thought it was a fun story. So we worked really hard. We were into this. Our spiritual leader, our senior scientist, had family that grew up in New Orleans, that he lived and breathed the Mississippi Delta. We started this work in 2006. By 2009, we had published a land building model that included all of not only the code, but then showed all of the parameters that we were using to do this. And this is just one of our scenarios. And we said, well, you could breach the Mississippi here and start to grow land. And those are just little mini Wax Lake deltas for scale. So this is not scientific, it's more artistic. What they decided to do, what we convinced them of, is that size mattered. You needed a big diversion. They decided to do it here at the Mid-Barataria base site. And I'll talk about that in a moment. But we were predicting values of land building. And you could put in, if you didn't like our subsidence values or our sediment flux values or our sea level, you could do whatever you wanted to and see what you got. It took over a decade then for planning, legal, and permitting challenges. But in 2023, they actually, it was all permitted, everyone agreed, and they broke ground on the site. All of us that were involved in this in 2006 went to New Orleans during Mardi Gras and had a celebration. Unfortunately, well, it's a good thing we had a celebration then, because unfortunately, people are a really, really complicated part of the Earth's surface system. And what ended up happening is groups decided they couldn't agree. And it just this summer, it was officially canceled. So that even though they had broken ground and had started to build it, it's been mothballed. So you never know what you're going to get, and that's one of the big challenges in coastal science is how do you communicate this to all the various stakeholder groups? It's a real challenge. Okay, so I talked about sand getting totally scrubbed from the coastal system, and that's because it was the Wax Lake Delta and the Atchafalaya are building out into a bay that has that really protects it from wave and currents associated with waves. So what happens, you can do the same thing on a coastline that's dominated by waves and wind-driven currents. Same equation here. You have to think about the sediment flux a little differently because things can go onshore, they can go offshore, they can go alongshore. There are a lot of different parts here, but nothing really changes. It helps you understand what's going on. So the question is, what do we know? So what I want to do now is just give you a sense of where I think we are in putting these things together through using just 2 case studies. But I'll begin with these great maps that were done here at the BEG by the Coastal Group, led by Jeff Payne. These are looking at erosion and progradation along the Texas coast over 2 different time intervals. Here you can see there's a whole bunch of green. So even at the high sea level rates we have had today and in the recent past, there's a lot of the coast that is prograding a little. And then there's a lot of the coast that is retrograding a lot. Even if you took 2 centimeters a year of relative sea level rise, and you took a sort of a foreshore, nearshore slope, you come up with losing, moving back. If you do the trig, a meter. Maybe you could say 2 meters, but it's somewhere in that range. So there's only a few colors on this map, right? Like particularly this one right here, that would be associated with just passive flooding of the coastline. All these other really hot colors that you see in here, the oranges to the reds, something else is going on. And again, it's this moving of sediment, and particularly moving sand, because Texas has a beach system, whether it's a barrier or not barrier system, all the way from Louisiana to the Mexican boundary. So we're going to look at sediment going onshore and offshore. And we're going to do this just with 2 case studies that I did with students here at the Jackson School. In the case of Hurricane Ike in 2008, we're going to look at storm surge that brought water and sediment from the ocean side landward. And then in the case of Hurricane Harvey, we're going to look at flow from land toward the sea. And mostly I want to give you a sense of some of the challenges we're up against, because if we're going to do this mass balance, we really need to know how much sediment's moving and when it's moving too. I mean, one of our fundamental problems with all these big events is we know what it looked like before the storm, and we know what it looked like after the storm. But when things move during the storm is going to control how much of it goes offshore, onshore, or alongshore. So that's something that we need to get a better definition of, hopefully. So shortly after Hurricane Ike, I convinced Phil Bennett, who had been is now an emeritus professor in the Jackson School, to fly out and look at some of these incredible overwash deposits, because I was looking for a place to study with a class. And you can see that all this sandy material that has been eroded from the beach area, and I'll prove that to you in just a minute, and deposited toward the bay. And this ended up being the one that says profile there. That's where we actually ended up doing our study. So thanks to LIDAR, bare earth LIDAR maps that give us high resolution TEMs, and the fact that we're collecting them commonly enough that we can look at before and after storms, we can get a sense of what amount of erosion and deposition there is. And there are a couple interesting things to see here. So the hot reds are erosion, the blues are deposition. So you can see a lot of erosion along the beach. There's sort of a little bit of deposition, and then the deposition gets really large further away, further toward land. And that's because the sediment's been moved off the old washover fan and now is filling space landward of the older washover fan. One of the things you learn right away in this part of the Texas coast is no matter what temporal or spatial scale you look at, you can't account for about half of the sediment. There's 50% more that's eroded than is caught up in the washover. So the question is, where did it go? And I still don't have an answer to that, but I know when it was moving, which is part of that answer. So that's what I want to share with you now. So here is the LIDAR from 2006. That's what the cross-section right there looked like. After the storm, this is what it looked like in 2008. That's the post-storm. And then if you just superimpose those, you can see the area where in gray, which is mass added, this is the interpreted Ike deposit. And that's the old margin of the washover material, and this is the new margin of the washover material. And then all of that in angry red is what's eroded, and it's quite a bit more. So we wanted to go out there and study that. And the LIDAR, this paper, we wrote it a long time ago. I'm sure the BEG was involved in collecting at least one of these LIDAR surveys. But I failed to look that up this morning. So we wanted to say, okay, we have a deposit. We think there's a deposit, but is that true? And what does that deposit look like? How accurate actually is that? Well, it turns out it's quite accurate. And it turns out I had really, really enthusiastic students. They dug a 100-meter trench. I've never seen this before. Here they're at the landward end of the trench, so that you're looking in toward the bay. And this is that profile right here. And then, and the next one, that's you're actually looking. We're now at the seaward end of the trench, and you can see the coarse, essentially lag deposit that was associated with the. You get an armoring on that area of minimal erosion, and the armoring is not coarse-grained sediment. Well, that's not true. There's this interesting beach rock that I don't quite understand, and it's a lot of shelly material, and so that's what's making. Excuse me. That's what's making that. So you can see here a couple images from, this is meter 62, 63, 63, 64. So those are adjacent to each other. And you can see very, very clearly the pre-storm surface, and it still has the grasses connected to the very immature soil associated that was growing on that older washover deposit, and a lot of planar stratification. But as you move toward the end of the system, you actually saw the little cliniform associated with the fan marching out into the bay. And what's really cool about this is that it marched out and up. So we measured that stratigraphy, and this fan actually ugraded half a meter while it was prograding. So that's a remarkable amount of aggradation while prograding. And if we make a guess about the depth of the water moving over this, which I'm happy to talk about you with later, and we can use this little break and slope from the top set to the foreset and track that elevation through time and compare it to water level data that was collected in the area and actually get a sense of when this storm happened. So what we're looking at here are two sea surface elevation measurements. One collected, the solid line is collected on the bay side. The gray line is collected on the barrier island side. Two things to notice: all the jaggedness on the gray water surface level measurement has to do with waves, not surprisingly. And the other thing is that the water surface levels get much higher on the bay side because it's the ultimate backstop. The island got totally inundated, and then the water just kept going right over the island, and it just grew to higher and higher elevations as it was pushed up against the land on the other side of the bay. And if we look at those elevations of our growing cliniform and we make some interpretations about what water depth was, we can find the part of the bayside curve, because it's growing into the bayside water level associated with those elevations. And what you see is that all of the sedimentation and then likely all of the erosion happened well before landfall. So it happened early, and it appears to have stopped once the island was totally inundated. So you had no accelerations associated with waves breaking and running up and down the island, that you actually stopped moving significant amounts of sediment. So that opens up, that's a constraint you can use to get a sense of how this might be moving in terms of alongshore and offshore. And it certainly suggests that the alongshore component is a much more likely candidate for the major culprit for the ability to being unable to balance mass locally than actually offshore transport, because everything was still very much getting pushed onshore everywhere here. So that is something that happened with the washover, or the seaward-directed surge. We're going to go into an area that John Goff and others know well at Port Aransas. The Marine Geology and Geophysics Field Camp comes here very often. MSI, of course, is there. UT's Marine Science Institute is there. And there were two sites that were collecting information about water levels and currents, one right at the Marine Science Institute pier, and then this is a NOAA tide station right here. And whether you just go to the primary data or you look at that's nicely summarized in John and his colleagues' paper in 2019, you get a sense that the seaward-directed flow that you have coming this way lasted for about 12 hours. And about 4 hours of that was before landfall, and 8 hours of it was after landfall. So, and you can see this is for a lot of that time, this is from ADCIRC, the sort of the go-to surge modeler. This is peak water surface elevations from their model, and the hot colors are higher elevations. These bands are 20 centimeter intervals, contours in water surface elevation. A 20 centimeter difference in water surface elevation is a big deal. That's a lot of change. And you can see that the wind blew and moved the water across the island, and eventually it raised to elevations where it breached a dune ridge complex right here and flowed out to the sea. So we want to get a sense of what that process looks like. This is on the island. This is just a a Google satellite image before the storm. Here is an Army Corps of Engineers LiDAR data. You can see this is the proto dune. The beach is out here in light blue. This is the dune ridge complex, and you have those two dunes right there, those ridges that get up to peak heights of 5 meters above sea level. So they're pretty large. And here we have then what happened after the hurricane went through. And you can see this is the data that was actually flown by the BEG, I think as part of a rapid, at least partially funded by a Jackson School Rapid Response grant. And then if you difference them, you can get a sense of how much terrestrial sediment was eroded away. But it's not just non-marine. These things actually cut below sea level. And you can also see this bright red thing here, which is actually a barge, which was on the leading picture. So it was ripped off of its mooring in the channel and floated almost all the way across the system. Now, here I have to apologize because I didn't realize it until late last night that the color bar of the difference map has been switched. Rather than blue being erosion, red is erosion here, and blue is deposition. Here's one of those large barges that was ripped up. And here are two profiles, one here, one here. The light gray is the pre-storm core data. The dark black is the BEG data. Here's the washover erosion. So this is the landward-directed surge and waves erosion. But these ridges were so high, and it didn't become a really big... Hurricane Harvey was one of those where we had incredible rapid intensification of the storm. So it was really only in the last 50 hours. It was a tropical depression 50 hours before it made landfall as a hurricane, as a Category 4 hurricane. So the winds were really high at the time of landfall, but in terms of fetch and growing a wind and developing a surge field, it was sort of modest. So these, you can see in light blue here, these are deposits associated with washover, this landward directed surge and waves. But both the erosion and the deposition is pretty modest, and it's just limited to the leading dune at the right at the edge of the beach. You can also see, comparing the pre and post topography of these dunes, is that they're eroded on the backside, right? Every one of them. So all those black arrows you can see they're sculpted. It's been taken off by erosion from flow going from land toward the sea. This one shows it. This one shows it well as well, in addition. So we had flows that we've documented the depth of which they were at least 2.5 meters deep. And we have flotsam organic vegetation rack line at 4 meters above mean sea level that I'll show you in just a minute. So here are some of those sculpted dunes. The flow, there's one of the barges sort of hidden in the corner. The flow is going this way. This is landward. This is seaward. All the erosion is on the landward side of this dune form. Here's Cat Wilson for scale. Here's the rack line at about 4 meters above mean sea levels. That floated into a protected area and gives us an example of maximum depth. So with these two LiDAR surveys, we can make these beautiful images of what these channels look like to get a sense of sort of how they form and how to think about them. So we separated them into big channels, and those were channels that actually cut across both dune ridges, and to small channels that ended up not making it across the second one and really have their head in the swale in between the two dune ridges. And they are totally controlled by pre-existing topography. All of the big ones, and there were wind gaps through the two dune ridges. So these are topographic lows in the alien dune structures, somewhere between 2.7 and 3.4 meters. There are no large channels cutting across that have elevations in that area that are all greater than 3.4 meters. So incredibly sensitive to pre-existing topography, which is pretty cool. And it continued to be sensitive to pre-existing topography. You can see these side channels that are coming off this channel right here. They're clearly associated with draining water from the swale between the two dune ridges. And if you look at this, I think these look like broccoli. Arissa thought they looked like baobab trees from Madagascar. But if you look at these composite heads, these sort of multiple amphitheaters making up the head of this channel, there is low topography separating each one of those heads. So it's not by chance. And that relief is like 50 centimeters. So their position appears affected by initial topography, and their final form also appears affected by that topography, which is pretty cool. So I'm going to have to speed up. So I'm going to speed up pretty dramatically, but we see a increase. This is just all of our channels, our 31 or so channels. The length and the width, they're linearly related to each other, which is actually just what you see if you look at breaches on levees, man-made levees. As they elongate, they widen. So it's not very surprising that we're seeing this result. And we know the sediment that was eroded from the terrestrial LiDAR. Underwater, we had to wade and collect the bathymetry, but fortunately, it's too cool not to do it. And some of these are really deep. They're like 2 meters below sea level. They're still 2 meters below sea level, the pools that are still there, because they fill in a very particular way. So here are the data for the heads. They actually look a lot like the head walls or the head scarps that people talk about with gullies and arroyos and their associated scour holes. We see exactly this form in these channels. And they all share the same properties of you're going from unconfined overland flow into a channelized realm. And they seem to have a similarity in shape, which hopefully will help us understand better. There's no change in the grain size between the necks and the heads. There is a change in the root density and the kinds of grasses we saw, and we thought, well, maybe this means that the grasses played a role in sort of limiting the position of where these channels actually grew to. And we needed to model this, so I'm going to skip this part in the interest of time. We did an Anuga modeling exercise. We could see, and I'll just show you, if it's not a morphodynamic model, but if you just look at the original topography, you can see that the hot spots in velocity, which are the browns, are right where the channels with margins, which are outlined right there, begin to develop. And if you etch in a proto-channel, you can see the distribution of high velocities very much mimic the final shape of the system. Now, we needed that sort of a model because we wanted to actually say something about the flux of sediment moving through the system. So we can measure how much sediment was removed thanks to John's analysis and the tidal gauges and the monitoring systems at MSI. We can turn that into sediment fluxes, and then we can compare that to what we would just get using a total load equation. And what you find is we went through a lot of reasonable parameter space with the total load equation, but the median values are almost exactly the same, and the means only differ by about 26%. So a couple things here. One is this wash out, or this outwash of the flow and the sediment that moves with it, is surprisingly well described by channel flow. It doesn't have a wave and tide component. You don't move nearly as much sediment during the washout as you do during washover. And so that's interesting. And we've now saw that at Hurricane Beryl as well. So I don't, that's the hypothesis that you don't. It's far from general yet. And the other thing is that since we can predict this with capacity sediment transport, it doesn't look like the plants are playing any role at all. This thing started cutting and kept cutting And the only thing that kept it from growing larger was the duration of the event. The hurricane is moving, and if it had stalled right over the coastal area there, we may have had a much larger channel. So it seems like the primary limit is exactly that. And these things fill up very slowly, and you can see an example of them filling up. We're now 8 years after that, and they're getting pretty close to full. There are 21 small ponds that equal 6% of the original area of these big channels that were cut below sea level. But they've filled up with sand, and now sand is going right out into the center of the islands because there's no topography to constrain it. Every washover event is moving the sand further and further out. So you're growing a part of the island that hadn't actually been accreting due to mineral sediment for a very long time. But still no aeolian growth. So these are still conduits that give direct access of the interior island to the sea. And so I'm gonna end there because I've run out of time. But this is a picture from 2021, one of our classes. There you can see they're all very busy. And you can see the channels associated with just normal high tide and washover bringing sediment in. So they fill in from they just fill landward, and they just prograde landward and finally fill up these pools. But we have now a challenge. We need to know about the mud capture and how it's connected to the plants. That's something that I'm particularly interested in. And then in the case of where we have wind and waves and wind-generated currents, we really need to understand why we cannot locally balance mass. I mean, and there's a good reason, offshore, alongshore, but it's just knowing that shouldn't surprise us. We still can't do much about true coastal resiliency if we can't balance mass. So that's the challenge. And the final thing I'll say is, sure, sea level's going up, subsidence is bad, but these things over here, and whether you can turn them on or they shut off, have as large, and in fact, a larger effect on our coastlines. So we should really be thinking about the flow of solids more than we do. So thank you for your attention, and I'm happy to take any questions.
Thank you, Dave. We do have time, so we should get these questions out. Thanks, Dave. Great talk. And thanks for the shout out too. In that pottery, the matic order, where you had the two pre and post profiles, you can see deposition. Yeah. It was very clear that there was unknown with very large quantity of eroded sediment in the shore face, because those shorelines had moved back. Can you comment on that component of the sediment?
Well, yeah, I can comment that on what we're trying to do now. I mean, I don't think my guess is it doesn't go too far offshore and that it comes back. And now with, the Gulf is turbid, but now with Planet and Planet Lab collecting almost daily data, and us in the Jackson School having a contract to access that data, there are days of low turbidity where you can actually get a sense of bathymetry. So that's something that a bunch of us are working on to try to actually understand exactly that. But I don't have an answer for you yet.
Start, Mark.
Yeah. Actually, just with this image here, but I was curious as you're talking about these channels and the infill, is that infill of the channelized space, is that episodics, or are those big storms that are creating the washover?
Yeah, I was going very fast at the end, but if you look, these two were collected within just a couple of weeks of each other. Hurricane Hannah happened, and Hurricane Hannah was a step function. It totally filled up some of these channels. So there's a persistent washover associated with high winds and high tides, And then there are storms that have had a more punctuated effect. Yeah. And there's a beautiful, you can see it actually, if you trench it, you can see it in stratigraphy. Problem is you get to the water level pretty quickly.
Okay, thanks. Great talk. Given how important the sand is in building land, how important do you think it is for historic land loss with the amount of sand that's trapped in upstream dams? Is that a significant impact on land loss or not?
So that's a great question and one that is hotly debated. If you don't have another place to mine that sand from, then it is a death nail. So like the Rio Grande in the last of the big dams, then the river flows out over carbonates, and there's nothing to erode and reestablish a sediment load. The Mississippi River does. There's a huge deflation area, and actually a humped convex up profile to the Missouri River downstream of the last dam, where it's collecting all the sediment it would have been moving beforehand. The Trinity River in Texas does exactly the same thing. You wouldn't know that Lake Livingston had been put in there because the river is mining that. So it really depends what the river is flowing over. And of course, that's a transient, right? Our guesses, our calculations from like the Trinity River, which is Texas, the most Texan river because it's the largest river fully in Texas. It has about another 100 years before that transient wave works its way through and the whole system will become very net degradation is our best guess. The Missouri, the estimates that have been published are about 1,000 years. So it's happily mining earlier quaternary alluvium.
I had to walk.